Welcome back, everybody. The next topic that we're going to look at is called the test for independence. And this test is actually the same as the test known as the homogeneity of proportions. And homogeneity is basically just a different way of word that means the same. In other words, equality of proportions. In this video, what we're going to do is we're essentially going to connect the test for independence to the goodness of fit in the previous videos. We're not going to do a hypothesis test. We're just going to motivate the idea. So here's how we can do that. Suppose that you're going to give 2,000 individuals a little strip of paper that is going to ask them two questions. The two questions are right here. They're essentially just asking, how happy are you right now? And then what is your current health? So just two short questions, and you're going to give that to 2,000 individuals. Notice that these questions are qualitative. And they can select from not too happy, pretty happy to very happy. And for health, from poor to excellent. If you summarize this, so let's say I select not too happy, and then I'm going to select good, then my one response is recorded in this table, because you can find me in the not too happy row here under happiness and under good. So my response gets recorded here. So I contribute to this 105. So 104 other individuals also responded with exactly the same combination here that I did. So a person that is in this group, they responded with pretty happy and their health is fair. All right, now what we're going to ask is that given this table, and we've seen this before, this was called the marginal distribution. So the total here are the margins. So it's called the marginal totals, row totals. The totals here, these are the marginal column totals. And so you get to essentially see how many times other people responded with good. So 935 people indicated good, just like me, but I was over here in 105 because I selected not too happy. All right, and so we saw these in chapter 5 as well. So our question is basically going to be very similar to chapter 5. In chapter 5, we said, are these categories independent? So there is this little question here that says, do you observe any trends? So if you look at this carefully, I'm not sure if you do observe any trends, but the best way to observe trends would be with a graphic. So a chart that depends on these categories. What we're going to do is we're going to do something a little bit different. We're going to go ahead and say, well, in chapter 5, I answered questions, or in the probability chapter, I answered questions like, is very happy and good, are those independent events? And if you remember how we did this, we essentially said you find the probability of somebody just being very happy. And we go ahead and we compare that to the probability of the same thing occurring, in other words, very happy. But this time, given that we know this person replied with good to the other question. And then if these probabilities are different, then good somehow has affected the occurrence of somebody replying with very happy. So this is how we showed that these were essentially dependent or independent events. Now we're going to go ahead and do something a little bit different. We're going to say, are the categories across the board independent? And so again, this is going to be the test for independence between these categories. So this should look familiar to you. We know that two events, P of A and B, are going to be independent if the probability of A times the probability of B is the same as probability of A and B, because this was P of A times P of B given A. So independence means that the conditional statement does not matter. And this is actually going to be the building block. So let's go ahead and assume independence. So my null hypothesis is going to be, I'm going to assume independence. And here's why. If I assume independence, then I can find the probability of somebody landing in here. So for example, I'm gonna call this P I-J. So row I, column J. Don't worry too much about this. I'm just gonna say the probability for each cell we can find by P-I-J. Or maybe let me pick one that's not at the beginning. Let's find this one, P-I-J. If I want to find the probability of this occurring, then that means that somebody replied with fair and they replied with very happy. So in other words, I'm asking, if I assume independence, what is the probability that somebody's going to respond with very happy and fair? So again, row I, column J. And because these categories are independent, so I'm just going to say that'll be the probability of, let's see, row I, so that's event I, and column J. By independence, again, because I'm assuming this is true, whenever there's an and, it'll become a multiplication. So it'll be the probability of row I times the probability of column J. Now, the probability of row I is actually pretty easy to find because remember, probability of somebody responding with very happy is the total number of individuals right here who respond with very happy, and that's over here. I'm going to call this A. So that'll be equal to A divided by the total sample size, which is here. And similarly, I'm going to multiply this by the probability of column J. So probability of column J, add up all of these values here. You get this. Let's call that B. So it'll be that number divided by N. So you can see here that under the independence assumption, the probability that a randomly selected individual will respond with very happy and fair is given by A times B over N times N. And the reason why this is important is this is the probability of observing row I and column J under the independence assumption. And look at what I'm going to do now. I'm going to say, well, if I already know the probability, then I can find, therefore, the expected count EIJ. So how many individuals do I actually expect to observe here under independence is equal to, remember, it was the probability times N. You just multiply those. Now, this actually works out really nicely. Check this out. P of ij we just found. It's A over N times B over N. And this time we're going to multiply that by N. But when N shows up in the numerator and denominator, you can cancel it out. So this actually just gives me A times B all divided by N. And luckily, if you remember what A is the row total. It's the total of row I. And B is 405. That was the total of column J. All of that gets divided by N. So we actually have this formula now that says, if you assume independence, you can actually find the expected count. So assuming independence, this means that the expected count for any row and column is going to be the row total times the column total divided by N. So just as an example, let's actually find the expected count for the entry right here. That's fair and very happy. So that is 405 times 1098 divided by 2,000. So throw that into a calculator and you're going to get the value 222 point, let's just round to one decimal, 0.4. And you can do this for every other cell. So if you're now going to look at this cell right here, all that would change is instead of 1098, you would replace instead of 1098, you replace that with 266 because that's the row. All right, so you can actually do this by hand. StackCrunch can actually do this also. So let me show you how to get this with StackCrunch, and then we're gonna summarize why that is important. Let me write it here just so that we have it in writing. To apply this in StackCrunch, we're gonna go to Stats, Tables, Contingency, and then with Summary. Because we have a summary. This is a summary of my sample. All right, so I'm gonna go, notice I already have my data in here. So I'm gonna go to Stats, Tables, Contingency, with Summary. Go ahead and select the columns, only the columns where you have data. So it was poor, fair, good, and excellent. The row labels were in var1. And that's pretty much it. You want to scroll down a little bit and it says, what do you want to display? And what we're going to display, now it seems kind of obvious, is the expected count. Press compute, and StackCrunch has performed that operation that we just did for each cell. So notice the cell that I was looking at was fair and pretty. In other words, pretty happy. Yeah, sorry. I'm like pretty. We didn't see that. But okay, in parentheses, you can see up here that that's the counts that observed. And then here you have the expected count. It turns out that by doing this, you have the expected counts of each cell. So notice they're in parentheses. And better yet, you actually get the test statistics for the test for independence. And you can see that the p-value is very small. That means you're going to reject the null. So this is all that I wanted to say. Here's why. If you copy all of these values in, I already I have a printout of this so I can see the numbers. Then what we end up with is you end up with a bunch of expected counts and observed counts. And that should be familiar because we've seen that in the goodness of fit test. So here it is. These are my expected. Here are the actual observed. So we're going to ask, is there agreement between the expected and the observed? And you can see that the answer is going to be no. So for example, this cell right here is 175, but I observed 271. That is 100 individuals different. 302 versus 247. So maybe that one's not so bad. Maybe about a 55 difference. And then this 297 versus 263, that's maybe kind of close. But you can tell right here is 34.6 versus 20. So there definitely is a lot of disagreement here. So once you've determined the expected counts, this is a goodness of fit test. And we will just proceed as before. All right, so in the next video, we'll do the actual hypothesis test for this data set.